When the feeder to a subpanel exceeds 100 amps, the National Electrical Code, specifically Section 310.16, becomes the governing reference for determining the appropriate wire size. It's important to recognize that Section 310.15b6 of the National Electrical Code has limitations applying only to feeders that are 100 amps or less. For practical application, consider the scenario of installing a 60 amp subpanel using NEC copper conductors. In this case, the minimum allowable wire size is number 4 American wire gauge. While the National Electrical Code doesn't mandate a specific temperature rating for the wire, it's widely recognized that the 75 degrees Celsius temperature rating is the most prevalent choice for residential construction. To elaborate further on conductor ampacity and selection, it's crucial to understand the role of conductor insulation temperature ratings. Conductors are rated for specific temperatures, such as 60 degrees Celsius, 75 degrees Celsius, and 90 degrees Celsius. These ratings indicate the maximum temperature the conductor's insulation can withstand under normal operating conditions. When selecting a conductor size, you must consider the termination temperature limitations of the connected equipment. Electrical equipment, such as circuit breakers and panels, is typically marked with a maximum termination temperature rating, often 60 degrees Celsius or 75 degrees Celsius. The conductor ampacity used for sizing must be based on the lowest temperature rating of the conductor insulation or the equipment terminations. For instance, if you are using a conductor with a 90 degrees Celsius insulation rating but the equipment terminations are rated for only 75 degrees Celsius, you must use the ampacity corresponding to the 75 degrees Celsius rating. Now let's delve deeper into the application of National Electrical Code Section 310.16. This section provides ampacity tables for conductors based on their insulation type and temperature rating. The tables list the allowable ampacities for various conductor sizes when installed in specific conditions, such as in free air or in a raceway. To use these tables effectively, firstly, determine the load current that the conductor will carry. This is typically the rating of the circuit breaker or fuse protecting the circuit. Secondly, identify the conductor insulation type and temperature rating. This information is usually printed on the conductor's jacket. Thirdly, refer to National Electrical Code Table 310.16 and locate the ampacity corresponding to the conductor size, insulation type, and temperature rating. Ensure that the ampacity is equal to or greater than the load current. If the ampacity is less than the load current, you must select a larger conductor size. It's also important to consider dating factors when conductors are installed in certain conditions, such as when multiple conductors are bundled together in a raceway or when the ambient temperature is high. These dating factors reduce the allowable ampacity of the conductors to prevent overheating. For example, if you have 4 current-carrying conductors in a raceway, you may need to date the ampacity by 80%. Now let's talk more about types of copper conductors. There are various types of copper conductors used in electrical wiring, each with its own characteristics and applications. Some common types include THHN, THWN, THW, and XHHW. THHN conductors are commonly used for general-purpose wiring in dry locations. They have a high heat resistance and are suitable for use in raceways and conduit. THWN conductors are similar to THHN conductors but are also suitable for use in wet locations. They have a moisture-resistant insulation that protects the conductor from corrosion. THW conductors are another type of general-purpose conductor that can be used in both dry and wet locations. They have a lower heat resistance than THHN conductors but are still suitable for many applications. XHHW conductors have a cross-linked polyethylene insulation that provides excellent moisture and heat resistance. They are commonly used for underground service entrance cables and other demanding applications. When selecting a conductor type, consider the environmental conditions in which it will be installed and the specific requirements of the application. Remember that the National Electrical Code provides detailed requirements for conductor installation, including dating factors, support methods, and protection against physical damage. Adhering to these requirements is essential for ensuring the safety and reliability of electrical systems. Sizing conductors correctly is paramount for preventing overheating, voltage drop, and potential fire hazards. Always consult the latest edition of the National Electrical Code and seek guidance from a qualified electrician when designing and installing electrical systems. Proper conductor sizing ensures the safe and efficient operation of electrical equipment and protects against electrical hazards. In addition to the points already discussed, it's also crucial to consider voltage drop when sizing conductors, especially for long circuit runs. Voltage drop occurs when the voltage at the end of a circuit is lower than the voltage at the source due to the resistance of the conductors. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The National Electrical Code recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. To calculate voltage drop, you can use the following formula: voltage drop equals 2 times K times I times D divided by circular mils, where K is the direct current constant, which is 12.9 ohms circular mils per foot for copper, I is the current in amps, D is the one-way distance in feet, and circular mils is the area of the conductor in circular mils. The circular mils for various conductor sizes can be found in National Electrical Code Chapter 9, Table 8. Once you have calculated the voltage drop, you can compare it to the recommended limits. If the voltage drop exceeds the limits, you must increase the conductor size to reduce the resistance and lower the voltage drop. There are also online voltage drop calculators available that can simplify the calculation process. Keep in mind that voltage drop is more significant for longer circuit runs and higher current loads. Therefore, it's essential to carefully consider voltage drop when sizing conductors for these applications. Furthermore, it's crucial to ensure that all electrical connections are properly made and tightened. Loose or corroded connections can create resistance, leading to heat buildup and potential fire hazards. Use appropriate connectors and tools for the conductor size and type. Follow the manufacturer's instructions for making connections. Regularly inspect electrical connections for signs of corrosion or looseness. Tighten or replace any connections that are found to be faulty. Proper electrical connections are essential for ensuring the safe and reliable operation of electrical systems. When working with electricity, safety should always be the top priority. Energize circuits before working on them whenever possible. Use appropriate personal protective equipment, such as insulated gloves and safety glasses. Be aware of potential hazards, such as exposed wires and energized equipment. Follow all safety procedures and regulations. If you are not comfortable working with electricity, hire a qualified electrician to perform the work. Electricity can be dangerous, and it's essential to take precautions to protect yourself and others from electrical hazards. Remember that the National Electrical Code is a comprehensive set of standards that provides detailed requirements for electrical installations. It's essential to stay up to date with the latest edition of the National Electrical Code and to follow all applicable requirements. The National Electrical Code is designed to protect people and property from electrical hazards. By following the National Electrical Code, you can ensure that your electrical systems are safe and reliable. In summary, when sizing conductors for electrical systems, consider the load current, conductor insulation type, temperature rating, dirting factors, voltage drop, and connection methods. Always consult the latest edition of the National Electrical Code and seek guidance from a qualified electrician when necessary. By following these guidelines, you can ensure the safe and efficient operation of electrical systems. Finally, I would like to touch on the importance of proper grounding and bonding in electrical systems. Grounding and bonding are essential for protecting people and equipment from electrical shock and fire hazards. Grounding provides a low impedance path for a fault current to flow back to the source, allowing the overcurrent protection device to trip and de-energize the circuit. Bonding connects all non-current carrying metal parts of the electrical system together, creating an equipotential plane that minimizes the risk of electrical shock. The National Electrical Code provides detailed requirements for grounding and bonding, including the size and type of grounding and bonding conductors, the methods of installation, and the points of connection. It's essential to follow these requirements carefully to ensure the effectiveness of the grounding and bonding system. Improper grounding and bonding can create dangerous conditions that can lead to electrical shock, fire, and equipment damage. Therefore, it's crucial to pay close attention to grounding and bonding when designing and installing electrical systems. In addition to grounding and bonding conductors, it's also important to use ground fault circuit interrupters, or GFCIs, in areas where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor locations. GFCIs are designed to detect small ground faults and trip the circuit, preventing electrical shock. The National Electrical Code requires GFCIs to be installed in specific locations to protect people from electrical hazards. When selecting GFCIs, choose models that are listed by a recognized testing laboratory, such as Underwriters Laboratories or all. Follow the manufacturer's instructions for installation and testing. Regularly test GFCIs to ensure that they are functioning properly. GFCIs are an important safety device that can save lives. Finally, I would like to emphasize the importance of regular electrical inspections. Regular electrical inspections can help to identify potential problems before they become serious hazards. A qualified electrical inspector can assess the condition of your electrical system, identify any code violations, and recommend corrective actions. Schedule regular electrical inspections for your home or business to ensure that your electrical system is safe and reliable. In conclusion, electrical safety is paramount. By following the National Electrical Code, using appropriate safety devices, and performing regular inspections, you can protect yourself and others from electrical hazards. Always prioritize safety when working with electricity and seek guidance from a qualified electrician when necessary.